kind of no good. I think linear algebra is very important. So some of you pick up bits and pieces of linear algebra here and there. When you take this course and that course, you have to know linear algebra. But linear algebra is extremely important for quantum mechanics. And some people even call quantum mechanics matrix mechanics, because you can replace all the differential operators, all the time derivatives and space derivatives with matrix algebra. And what you need to do then is just to do matrix manipulations. So you can learn a lot. You need to learn linear algebra in order to understand quantum mechanics. So I'll go through some of the revisions needed. I guess most of you have not had a course in linear algebra, right? Since it's not required. Am I right? It's not required. You have a course in DPQ, you might have a course on special functions and that kind of thing, Leibniz polynomial, but not a course in linear algebra, I think. It's only an elective, right? So let's review the fundamental knowledge you need in linear algebra in order for you to learn quantum mechanics. And if you read David Miller's book, he actually goes through some detail on teaching linear algebra to engineers. Okay, he actually tells you how to do a matrix vector multiply with a matrix vector product. Okay, so all of us know what a matrix is. When we have a matrix A, it actually is a whole bunch of numbers, A1, A2, A1n, and then you can go down to A21, AN1, and then you can go all the way down to ANN. You probably have seen this from some courses. If you do a circuit theory course, you need to have a Z matrix, for instance. And that Z matrix has to be something of this form if you learn circuit theory. Then how do we do a matrix vector multiply? What does this mean? A dot B. Okay. You probably have had this exposure before. And what this means is that the vector V is a column of numbers, V1, V2, Vn. And so this has to be length n. So we say that this is n by 1. Okay, this is an n by 1 matrix system. You can think of a column vector as a special case of a matrix. Matrix can be n by n, but also can be of other dimensions, non-square if you want to. Okay, it can be n by n, but most of the time we deal with square matrices because they're easier to deal with. They have an inverse. Whereas a non-square matrix may not have an inverse. This means this thing over here. If I write in notation, then this is just Aij, Bj, j equals to 1 to n. Okay, this gives you the ith element of a column vector. This is something that produces a column vector, and it gives this ith element. So if I were to look at the ith element of this column vector, which I represent as B in its ith element, it can be written in this very concise notation, and that's what a matrix vector multiply means. And this is what you have to program when you go to the computer to program it. And Einstein actually was very lazy, or maybe some people was very lazy in writing this summation notation. So he often just write things as Aij, Bj. And it's understood that repeated indices means a summation. So oftentimes in many textbooks, especially physics textbooks, they neglect to write the summation. And this is understood. This is called indicial notation, or index notation, or Einstein's notation. Einstein loved to use this notation. Okay. So this is just a matrix vector product. And of course, you know how to do a vector-vector product. And you cannot multiply two vectors together very easily. Okay, so there are only certain ways that they can be multiplied together. You can think of, if I have a vector W and a vector V, if I want to multiply them together, W might consist of a column vector, something like this, and then V might consist of a column vector, something like this. In order to multiply them together, you can actually use the rules of matrix vector multiply. You can think of W as a matrix which is very thin, okay? A n by 1 matrix system if you want to. And in order to multiply this together, you have to turn this around and make it lie on this side. Okay, this is called W transpose. W transpose. And then if you multiply two vectors together, one way of achieving that is just to do this together, which is the same as putting this on the side and then multiply this as it's standing vertical. And if you multiply this together, it's very similar as you're doing this. Okay, this gives you a scalar number. A scalar number may be B. Okay, has no dependence on notation anymore, and it's just equal to W I B I equals 1 to n. That is what the vector-vector product is. And you have other kinds of vector products where you might denote something like V conjugate dot W. V conjugate has the meaning of V transpose plus an additional operation followed by conjugation. Conjugation means you convert, for electrical engineers, you convert all the J's to minus J's. For physicists, you convert all the I's to minus I. I is the square root of minus 1, so it's J. Okay, so electrical engineers and physicists use a slightly different notation. So whenever you see a J, just replace with minus J. That seems to be the simplest thing you need to do when you do a complex conjugation. Okay, so the conjugate transpose or a Hermitian transpose means this. And we can also do matrix vector product, vector-vector product in this manner. Okay, this just means that. Okay, the good thing about conjugate transpose is that when you have two vectors that are of the same kind, if you do it as inner product, this is also called inner product. If you do an inner product of these two vectors, then if I use this knowledge that I have written up there, then it's equal to that. And VI conjugate times VI, what do you know about its special property?
It's real.
It's always real and it's always positive. Okay, so this is the same as VI squared, magnitude squared. And this sum is always less greater than or larger than 0. Okay, and mathematicians have a name for this. This quantity is always positive definite. It's always positive definite, and that's very good because it's never negative. Whereas if you take this inner product, and if you end up with doing an inner product like this between these two vectors, you get a whole bunch of numbers which could be complex numbers. Okay. If these are complex numbers, this cannot be ensured to be a real number, and this can be complex. Okay, that's no good. That's no good because then we cannot measure length. Okay, this can be used to measure the length of a vector because length is a positive definite quantity. Okay, so this gives you the concept of a length. And this kind of inner product is good in that sense. Okay. Are there any questions so far? I think that a lot of this you already know. You already know this by having taken so many courses in ECE, and you have come across having to use this knowledge. Okay. And one of the other things that you should know about matrix algebra is that if I write down something like this, it's ambiguous, right? It's ambiguous because it turns out that matrix product is associated. It doesn't matter which one you do first. Okay, you can actually prove this very easily by using this notation for matrix product. You can say the Aij, Bjk. If you say Dik, if I were to sum this over J, if I define a matrix product to be, that is just an extension of a matrix vector product. The matrix product gives me two indices, and that is a matrix element. Okay, so this is the same as saying that A dot B equals C. And you can go through this algebra, which I will not go through, to show the associative property of matrix product very easily. Okay, and another thing that is very important that you find also in your electrical engineering courses is that this is not true. This is often true for scalar numbers, but if you have two matrices, this is generally not true. Okay, this is called the non-commutative property. Okay, unless the matrix is very special, then this is not true. You have to have a very special kind of matrices before this is true. Okay, and sometimes in quantum mechanics, we do come across matrices that are commutative. Most of the time, matrices cannot be assumed to be commutative. So a Hermitian matrix, when we take the dagger, it implies that for every matrix element, you actually do a transpose and then it conjugate transpose, very much like what you do for the V dagger over here, but you apply to every element of the matrix. And then what is the transpose operation? Transpose operation means that you replace Aij with Aji. Okay, that you probably have come across before. Okay, you just swap the matrix around. Say if this is your matrix, and you want to take its transpose, you just swap the upper triangle with the lower triangle, and then swap the elements. Okay, that is the transpose operation. And how many of you is not clear or are not clear about this transpose operation? Okay, so a Hermitian transpose is just this operation over here. Okay? So, yes, yes.
What's the difference between vector product and inner product?
Okay, vector product is also an inner product. Okay, this is generally used in mathematics. Okay, inner product between two vectors, and there are of course something called the outer product. Outer product is when you do things like V, W transpose. Okay, then V is the column vector. This means that you're multiplying column vector by the transpose of a vector on the side. And we know how to multiply this kind of matrices. You would think of this as n by 1 matrix and 1 by n matrix. We generally know how to multiply non-square matrices. So it's very much like the multiplication of two non-square matrices. Okay, and you get I'm running out of notation over here. Let me call it a L. Okay, matrix L. And this matrix L will be n by n. Okay, so if you do an outer product, this is called an outer product. You get a matrix. If you do an inner product, you get a scalar. Okay? And vector product is often applied by physicists to take the inner product between 2, 3 vectors. Okay? But they also can be applied to vectors of any length. You can also call this a vector product if you want to. But you have to be careful because there are different kinds of products. One being an outer product, the other one being an inner product. And when you say product between two vectors, you better be careful as to which one you're referring to. Okay? So are there any questions so far? if not, a matrix is Hermitian if A conjugate transpose is equal to A. These kind of matrices are called Hermitian matrices. And if a matrix is equal to its transpose, this is called a symmetric matrix. Okay, a symmetric matrix. You can see that if its transpose is itself, that means that this element must be equal to that element, this element must be equal to that element, and so on. This matrix has a kind of symmetry along this diagonal. Okay, that is the meaning of a symmetric matrix. But if it's Hermitian, it has something more than that. It says that this element is not equal to that element, but they're conjugates of each other. This element is conjugate of this one, this element is conjugate of that one. Okay? For instance, this matrix 1, 3, 3, 1 is symmetric. This matrix 1, 3 plus, let me use I instead of J. Okay, is that okay? 1 plus 3, 3 plus I, 2. This is a symmetric matrix, but not Hermitian. Okay, this is symmetric, but not Hermitian. Not Hermitian. Okay. However, if you were to write a matrix like this, 3, this is Hermitian. Okay, so you see this kind of matrices. This matrix is symmetric. Is this also Hermitian? It is. Okay, this matrix is both symmetric and Hermitian. Okay, it's both symmetric and Hermitian. So you can see 3 kinds of matrices over here, and they all appear in quantum mechanics. Okay. And of course, a matrix has its inverse, and the finding of inverse is a very elaborate process, and I won't go through how to find an inverse. It involves very complicated mathematical and computed algorithm. Say if I have A dot X equals B, and if A is a square matrix, in order to solve this equation, I have to find its inverse. A inverse has a property that when you multiply by A, you get an identity matrix. There's a definition of an inverse. Okay? So I can multiply this equation by A inverse, and then I will get A on the left-hand side equals to A inverse dot B, but then A inverse dot A is identity. Identity matrix is just a matrix having the property that when it operates on anything, identity matrix operating on any vector gives back the vector itself. That is the meaning of identity matrix. You can construct such a matrix very easily. And then you put 0 here. This vector operating on any vector will give back the vector itself. You can verify this yourself. Okay, but there are other kinds of identity vectors in this world, but this is the simplest one. Okay, because of that, then you can solve this equation by arguing that A is just A inverse dot B. Then finding A inverse is a long story. Okay, how do you find it? For 2 by 2 matrices, most of you can do it by hand. For 3 by 3, most of you can still do it by hand. For 10 by 10, don't do it by hand anymore. Okay? Use MATLAB, computer program, or something. And computer scientists and mathematicians have written down algorithms on how to do them. And finding the inverse will follow the name of Gaussian elimination, for instance. Cramer's rules or something like that. And you will use this kind of algorithm to find its inverse. It's not an easy task. And if this matrix is n by n, And if it's densely populated means that every element of the matrix is non-zero. Finding this requires CPU time proportional to n to the power of 3, which is not very good. It means that if you make your matrix dimension 10 times bigger, your computer time goes up by 1,000 times. If you make it 100 times bigger, it goes up by 1,000,000 times. Okay, it scales much worse than Moore's law. Okay, if you want to make something, the computer becomes useless, just ask the computer to invert the matrix using Gaussian elimination of Cramer's rule. Okay, you can get the computer to come to a halt. Okay. So another thing that comes up quite useful in quantum mechanics is actually unitary matrices. Unitary matrices are a special kind of matrix having this property that its conjugate transpose times itself gives you the identity matrix. This means that its conjugate transpose must be equal to its inverse. Okay, from this property that we have just learned over here. Okay? And many matrices in quantum mechanics have this property. Okay, so this is a property that you should know. Okay? And another property of a matrix is actually its determinant. Finding the determinant of a matrix is a very difficult thing. Gives you a scalar number. It also follows from an algorithm. And if you have a 2 by 2 matrix, it's very easy. A 1 by 1 matrix is very simple. It's just determinant of a scalar number is itself. Okay, if it's 2 by 2, A11, A12, A21, A22. If you take this determinant, it will be A11, A22 minus A21, A12. Okay, that is the determinant of a 2 by 2 matrix. It's a scalar number, and then there will be a determinant of 3 by 3 matrix, which is slightly more complicated. You have to have certain rules, and then when it comes to 4 by 4, there are certain rules of finding this. I don't remember those rules. Okay, I just learned them once and forgot about them. And you call a computer program to do that. Okay, so there are certain properties of determinant that you should know. Determinant of the identity matrix is 1. Okay, in that case, it's quite easy to show. And then you can show that the determinant of the transpose of a matrix is the determinant of itself. Transposing a matrix doesn't change its determinant of value. And that the determinant value of A dot B is equal to the determinant of A times determinant of B. Okay? And then determinant of A inverse is 1 over the determinant of A. Okay? And if lambda is diagonal, if lambda is a diagonal matrix, then lambda is a matrix that looks something like this. Lambda 1, 1, lambda 2, 2, lambda n, n, and then 0 on the off diagonal. And if you take the determinant of this matrix system, it's just a product of the values on the diagonal. Okay, just take those values, multiply together. That gives you the determinant of this matrix. And it also can be proved that if you know the eigenvalues of a system, okay, let's I guess Ian told you what the eigenvalue of a matrix system is, but if you do know the eigenvalue of matrix system. For instance, if you were to find that an eigenvector has this property that when it's been multiplied by a matrix, it is just a scalar times itself. This is only possible if this is true. I can replace the right-hand side with this thing, and then I can say that if the above is true, then this must be true. Okay, this must be true. And this is true only if determinant of this is equal to 0. Okay? The determinant of this is equal to 0. And again, you go through some very complicated algorithm to find the determinants. You can use a very simple algorithm to find what it should be if A is 2 by 2, but when it goes to a larger dimension, the algorithms are rather complicated. Okay, what this gives you is actually a polynomial equation, lambda n, A0 plus A1, maybe I should write the other way around, A0 plus A1 lambda plus an lambda n is equal to 0. This equation finally can be reduced to that form. Okay, an n order polynomial in lambda, lambda being a scalar number. And how many roots would this polynomial have? It will have n roots. Okay, it will have n roots. So in general, if you solve this equation, you have n roots, giving rise to n possible values of lambda. And those are the values with which you can find a solution like this. Okay, if you plug in the values that you have found here into this first equation, then you have a chance of finding lambda. Then you go back to this equation and say, if I want to find a specific eigenvector associated with a particular lambda that I have found, and that would be the eigenvector that satisfies this equation. Okay, and that eigenvector lies in what we call the null space of this vector. Okay, so if you have a vector b dot x equal to 0, this is only possible if x is in the null space. And that concept is often taught in linear algebra. Okay, when a vector has this kind of property, that means that there exists a vector x such that when multiplied by b gives you 0. This means that this vector b has a null space. If this is possible, then you can go through an algorithm to find this b. It's again not trivial. When it's 2 by 2, it's quite easy to do. When it's n by n, finding this vector is not trivial. And you can go to a computer program to find it. Okay? So you find those eigenvectors. And it turns out that the determinant of the determinant of a matrix is also the product of its eigenvalues. Okay, that could be true. If you found all the eigenvalues, if you want to find a determinant value, you just go to this and you can find that. Okay. And if determinant of A is equal to 0, it means that there exists a vector u such that A dot u exists. Okay. There exists such a vector u such that this is true. If the determinant of A is equal to 0, and then you can prove that if you multiply the matrix by a constant c, then its determinant value is just c to the n determinant of A. Okay. So I just want you to commit some of this knowledge to your memory. Proving them can be found in most linear algebra books. If you are interested in reading about the proofs, but this kind of properties are often used in quantum mechanics. Okay, so I present them without proof, and as an additional knowledge, you might want to learn them by yourself. Okay. Are there any questions so far?
Yeah, what's the physical meaning when the eigenvalue is 0? Well, it has a meaning, right, for circuit or something?
Eigenvalue is 0 means that in physics, in many occasions, when eigenvalue is 0 means you have a resonance condition. Okay. Say for instance in circuits, all of us are electrical engineers, or most of us are. So given any complicated circuit, you can derive this equation. Okay? And you can derive this equation, say, with a voltage source and then very complicated circuits. And this equation for something very complicated will look something like this. Okay, something you can derive. All of us know how to derive this equation. Say, if I were to take the voltage source away, I take the voltage source away, replace it with a short circuit, replace it with 0 volts. What happens to this? If there's any voltage source in this, I will have a column vector all over the place, right? All of you are great in solving circuit problems. ECE 210 kind of thing. So if I set the right hand side to 0, means I remove all the voltage sources in the system. Okay, so I have this equal to 0. When can I find a non-trivial solution? I is a current over here for electrical engineer, a non-trivial solution. And that is only true if this is true. Okay, this is true. And oftentimes, you have to look for the solution of this off the real axis. You have to find an omega. This cannot always have a solution. It can only have solutions at certain omegas that this equation is satisfied. Oftentimes that omega might even be a complex number. Okay, you will go about searching for this solution. And you have found that omega, then you have found a non-trivial solution. And that solution is the resonance solution. Okay. Or the resonance solution. Okay. And this is just an example of what a zero eigenvalue means. Okay, zero eigenvalues means a non-space solution or a non-trivial solution. And for circuit problems, it corresponds to a resonance condition. Okay. So let me see what else I want to say. So, if A is summation, implies that lambda is real. Okay, this fact can be proven quite easily. Let me just prove that. A dot x equals lambda x. Say if I found the eigenvector that this is true. Okay? And then I find another eigenvector. Let me see. Not a very good notation, but I use it anyhow. Lambda j, y j. Okay, I found two eigenvectors that this is true. I take the transpose. Let me do this. I multiply this by yj transpose. I'll multiply this by xi transpose. Conjugate transpose, sorry. I'll do a conjugate transpose here, conjugate transpose here. Okay, and you know how to take transpose of a product of matrices. Okay, if you have A dot B dot C, if you need to take this transpose, it's just equal to C transpose dot B transpose dot A transpose. You can convince yourself of this very easily. Okay, you just go through some of the properties of matrices. This can be actually proven quite easily also. So this applies to conjugate transpose as well. You will replace this with daggers. Okay, you can prove and convince yourself of this quite easily. So if I were to think about this now, if I take the first equation and take its conjugate transpose, I guess I'll do it in my head, okay? Maybe a little bit fast for you. If I take the conjugate transpose of the first line, okay, I will get xi conjugate transpose dot a conjugate transpose dot yj. I take the first line and conjugate transpose on the left hand side. This multiplies by that as well, okay? And if I have a number lambda I, and if I take its conjugate transpose, okay, let's assume that that lambda is not real. Okay, its conjugate transpose will be just itself with the conjugation up there. And then up here, xi conjugate transpose yj on the right hand side. The first line, I take the conjugate transpose. I have that. And then the second line, I say that A conjugate transpose is itself because A is summation. So if you look at the left-hand side of this line, it's actually equal to the left-hand side of the second line. Can you see that? Okay, and you subtract the two equations. If I take, say, 1, 2, and then 3, I take 2 minus 3. Okay, the left-hand side will cancel. Okay, the left-hand side will cancel. I have 0 equals to, then I have xi conjugate transpose yi. On the right-hand side, I will also have that on the right-hand side. So I have lambda I conjugate transpose minus lambda j xi conjugate transpose yj. Okay? So this line, the last line, proves two facts. One fact is that if xi dot yj is not equal to 0,